So wait, I was out on my canoe at sea the other day.
Of course.
And I was looking at the morning sky and I was like, oh, that's blue, that's funny. And there's a rainbow, I was like, oh, I wonder how that goes. And then I capsized.
You okay?
And there was a shark and I was like, oh no, how do I fight it? And I went, I don't know how to find out how strong weak acids are.
Ah,
yeah.
You can learn that now.
Oh, okay, that's cool.
Let's get on with that.
Alright.
So it starts with thinking about the difference between a strong and a weak acid.
Yes, this is really a RICO AS, but a strong acid completely dissociates.
Yep. Using
Using this idea, we can make a few sort of assumptions / leaps from here.
So it's going to completely dissociate into that.
Yeah, so our HA, which is our model acid, will always have a H and an A part, and it will form these two things.
Absolutely. So the assumptions Trip was talking about that we can make.
Basically like a stoichiometry relationship. As there is going to be like 1 mole of this, there'll be 1 mole of that, and 1 mole of that. But the important relationship is here. It's going to be very handy.
We can say that the concentration of the HA in the original solution is going to equal the concentration of the H plus in the product solution. Yeah. And that will be more important in a second. Let's remind ourselves of the acid dissociation constant equation for a strong acid.
Yeah. So the acid dissociation equation for a strong acid, have you got my pen? Yes. Ka is equal to,
and it's products over reactants,
yeah,
nearly always are. So H plus times the A minus over HA. And these are the concentrations of each of these things. Will give you the Ka. And as we said in the previous video, normally you'd be asked to work out the H plus.
Yeah, and they'll give you the rest.
Yeah. And what that can be used for, if we go on a next step, is our equation I've wrote up here, which is working out pH.
So then, if we have the amount of concentration of, say, our hydrogens, our pH, we do go through how you get to this in another video, I think. Yes. So you can check it out if you don't know.
Yeah, check out our pH video for this and the actual relationship if you don't do maths. And you can use that equation. That's normally what the question would ask you to do, is find this. But now we go for a weak acid.
We do. So if we had a weak acid...
Yeah, we could still call it HA, because A can represent anything.
The only difference is it forms an equilibrium reaction as opposed to just a straightforward reaction.
Which does change things.
It does change it, because you can't then assume that the concentrations will be the same, because the midpoint of the point where you live in the middle isn't going to be in the middle, that's the problem.
Yes. So, because it doesn't fully do everything, some of that will be formed back into that. Not all of that's going to disappear, essentially. That's what we're going to say.
So you have to form a sort of different relationship here.
You do. So the HA you started with, the concentration of that you put into the mixture before it reached equilibrium. After it's reached equilibrium, it won't be equal to H plus.
No, but it will be equal to HA minus H plus, because the other ones would be turning back into HA, so the ones that it wouldn't be.
Exactly. We can make another assumption. We can make the assumption that the concentration of H plus on the product side is still going to be equal to the concentration of the A minus, the rest. Each one that dissociates is dissociated, that's it, partially dissociated, so they're going to be equal on that side.
Yeah. So using these two things, we then try and form a Ka equation.
Absolutely, so I'll put it in blue. And we're actually going to do 2. We're going to go for the first one, and it actually simplifies down, which is good news.
Yeah, which is nice.
So we've got
we start with Ka, and as always, your products over your reactants. But you've got quite a few sets of things.
You do. Your products is still your H plus and your A, which is still really going to be, well, it still is going to be H plus times your A minus.
Yeah. But on the bottom, you'll have HA minus H plus.
HA minus H plus. And now that's a mean little equation.
That is mean, but you can simplify it down. Firstly, these two things are equal. So that's the same as writing one of them
as the other one. You could either say A minus times A minus, that would give you the same answer.
And there's a simple way of writing that, which is H plus squared, or A minus squared.
Exactly. So that then means you need to know less, because as it stood then, to work out your H plus, you'd have had to know that, and A. Whereas now, you don't need to know what A is.
And then, we can try and get rid of this one.
By making a small assumption.
Yeah, you assume that the concentration of that in your solution is so low that it makes no difference anyway.
Yeah, so you just essentially ignore that. So the equation will just simply become H plus squared over HA, and that would be that. So it's slightly different to this one, and it's based on these model assumptions we're making, and that would be That'll be your acid dissociation constant.
Yep, and that's for weak and that's for strong. So now we go through a couple of work examples.
Yep. If the same thing's going to happen, they're most likely to ask you for this H+. So you'd have to rearrange times a Ka by Ha, then square root it all. So let's just get on with that and see where it takes us.
So, start with a strong acid.
Absolutely. I don't know where my board rubber's gone though.
Oh, you've dropped it.
I did.
I've lost everything. My red pen is by IT. It's a complete disaster.
Well, who did you go canoeing with?
Oh, sharks mostly.
Oh yeah.
So if we have HCl, the strong acid, we know it completely dissociates. That won't be an equilibrium reaction.
So we know that the HCl, we can write an equation. This might be a good step in your exam.
Yeah.
It's going to go to H plus Cl minus, fully dissociates.
And then you can do your triangle of dots, which means therefore, you can say your concentrations will equal.
Exactly. So.
And that's a good step as well. So explain why you're doing each thing.
So we can say HCl, like we did before. Our assumption is equal. That's supposed to be a square bracket. To the concentration of H plus.
So say we know that the concentration of HCl is 1.22 times 10 to the minus 3,
okay,
for example.
If we know that, then we therefore know by this assumption that the concentration of H plus ions formed is the same thing. So if you're trying to find out the pH of the HCl,
we can then put it into our equation at the top, where pH is equal to
minus log, and then the concentration of H, which we know, so this assumption is the same as the concentration of the HCl.
Then we can do that.
And that will give you the pH of the initial HCl. How handy is that?
That's very handy, but what about weak acids?
Well, that's where we have to use our new formula and assumptions.
It is.
Have you got an example for that?
I have got an example of that.
Oh, fantastic.
So if we have a weak acid, say HNO3, that will form an equilibrium relationship as opposed to a straight relationship.
Yep.
So
which acid did you?
HNO3.
HNO3.
So that will still, again, form into H plus, but NO3, but for equilibrium.
Yeah.
And we know a few things. You need to know more for this one. You need to know the concentration of that. So say the concentration of that is 0.05.
Yep. You're going to be given, or most likely to be given, the concentration of this.
Yeah, and you have to know your Ka as well.
That's the only difference with this one over the other one, because of our equation. You need to know two things to find out the third.
So if you know those two things, then you can put them into an equation that we had before.
So we have Ka is equal to H plus squared.
Yeah. Important thing to remember, you will need to square root later, over HA.
So HA in this case is that.
Yeah.
So
now we know these things. So we can't assume the concentrations are equal, we only know the concentration of that, so we can rearrange it.
Yeah.
So the Ka times HA will equal our H plus squared.
Absolutely, just like that. And then you can square root both sides.
You can square root sides.
Now I'm actually going to put the values in. So we're going to square root Ka, which we know.
Yeah, 4.7 times 10 to the minus 3. It's important to use brackets here.
Yeah.
Then times your other half.
And the Ka is, we've also know, is 0.055.
And that will equal the concentration of our H plus.
Yeah.
And then once you have that, then you can put it into the log relationship.
And then it's just the same thing, minus log of whatever you've got here. And again, it will be giving you the pH of this initial acid.
Yeah, it will.
And that's really useful if you've got a bottle of acid and you think, oh, what's the pH on that?
Yeah.
I've got a question though, because you've asked a really good question that's given us a video. I've got a question. Why did you want to know?
Oh, you see, Wayne, I've got this penny and I want to make it really shiny.
Oh, you need to speak to my good old friend Barry Scott.
Ah,